Hello, everyone. Welcome back to my DP Chemistry curriculum. Today we're going over Lesson 26, Reactivity 2.1.5. You may have noticed we skipped 2.1.4, but honestly, that's percent yield. It's kind of ap- appended to 2.1.3. So we're going to be going over atom economy as a measure of efficiency in green chemistry. We'll kind of only talk about green chemistry at the end. We're going to be able to calculate the atom economy from the stoichiometry of a reaction, their stoichiometry. We will include discussion of the inverse relationship between atom economy, and wastage, and we have the equation for economy within the data booklet, so you don't necessarily need to memorize it. So first off, what is atom economy and why do we need it? Well, in the previous lesson, we learned about percent yield, and percent yield kind of told us how efficient a reaction was. But that's not necessarily true. You can have a really efficient reaction with like 98% yield, but maybe you're producing a byproduct. Maybe you're also producing toxic waste. Now, you may have a really efficient reaction. Like this is very efficient. You're getting a lot of the product that you want, but you have a byproduct that you don't want. And so chemists may turn to this type of reaction that has a very high efficiency, but you're producing something harmful as non-efficient. So we have atom economy as a new metric for efficiency. What this actually defines is a measure of reaction efficiency in which, let's say, not in which, let's just say a measure of reaction efficiency which compares molar mass of your desired product. It's what you actually want. And what you're going to do is show that molar mass of your desired product as a percentage. We like percentages when talking about efficiency of molar mass of total reactants. What that means is we're comparing our final product to what we put in. So we're trying to actually see how much of our reactants became our product because that's true efficiency. What we're really trying to do is we're trying to avoid byproducts with atom economy. Byproducts. Byproducts are just anything that were not your actual desired product. Byproducts are essentially waste. So there's a formula for this, the one that's in your data booklet, percent atom economy or econ. That's going to be your molar mass of your desired product divided by the sum of the molar mass of each reactant. And we're going to multiply that by 100 to get a percentage. So the best way to figure this out is to just try an example. So what we'll do is we'll go over the three steps. It's kind of self-explanatory, as you can see via this equation, but I'll write them out anyways for those who like a procedural view. So calculating atom economy, I'm just going to abbreviate that. So first, we have to calculate molar mass of product. Next, we have to calculate the sum of the molar mass of each reactant. And then we just plug into equation. And I mean that one up there. So let's go ahead and do an example on this. So iron can be extracted via this reaction. 3 carbon dioxide, or sorry, 3 carbon monoxide gas plus Fe2O3, so that's iron oxide, which is also known as rust. And when you add heat to that, you make carbon dioxide plus iron. Now, one thing I want to point out is in our equation up here, in our, not equation, in our steps, something I did not include but should include is that this is molar mass of the product times the coefficient. And this is molar mass of each reactant times their coefficient as well. Those coefficients are important to our ratio as they actually indicate how much we're producing. They're part of that mole ratio and reacting ratio that we discussed in earlier sections. So using this, we're going to follow the steps. Step 1, we want the molar mass of the product. So our product is iron. Iron has a mass of 55.85 as seen on the periodic table times its coefficient of 2, giving us 111.70 grams mole inverse. Remember, this is a molar mass. We'll keep our units. The sum of the mass of our reactants, that is going to be our carbon monoxide, which is 12.01, plus our oxygen, 16.00, times our coefficient of 3. Plus, now Fe2, that's again 55.85, but within the parentheses, I'm going to multiply by 2 for the subscript, plus 16.00 times 3. Remembering that this is CO and this is the molar mass of Fe2O3. The sum of this is going to equate to 243.73 grams mole inverse. So now all I have to do is step 3, plug all this into my equation. 111.70 divided by 243.73 times 100, and I will find that I get an atom economy of 45.83% efficiency. Now, to me, that is a not very efficient process. So this would be something that we would need to look for other processes for which we can extract iron than reacting it with carbon monoxide, because we're getting very, very, very little efficiency within our reaction. So a couple key things to keep in mind when looking at atom economy. Usually, more byproducts equals less efficiency, which seems kind of obvious because if you have more of that excess stuff, then that's going to take away from mass that could be converted into your desired product. But we can take this even further. If we use the law of conservation of mass, we can find that if we only have one byproduct, or one product being our desired product, one product or no byproducts, that would equate to 100% efficiency. So if your reaction is only making the thing that you want, that's perfect. That is a reaction you want to use, no byproducts. That's fantastic. So we're going to end this with a little bit more practice because practice is how you're going to get better. So what I'm going to do is provide you with a situation and 2 reactions, and I want you to do 2 things, and we'll discuss when we get there. So for production of table salt, which is sodium chloride, NaCl, for production of table salt, generally there are 2 reactions. So which reaction has a better atom economy? So let's look at reaction 1. Reaction 1 takes sodium bicarbonate, NaHCO3, which is just baking soda, and it does it aqueous, so we've dissolved it in water, plus hydrochloric acid, again aqueous because it's within water. And upon the reaction, we do get table salt, NaCl, and this will also be dissolved in that water. We get water as the carbonate reacts with the chloride, but we also get carbon dioxide as a gas. This is already balanced, nothing else needed. Reaction 2 has sodium hydroxide, NaOH, plus hydrochloric acid, oh, aqueous, almost forgot state symbols. Never forget your state symbols, the DP will take away for that. And you will create, again, sodium chloride, that's our main product we're looking for, plus water. So before you go off and try this on your own, what you want to do first is just try and assume which of these reactions is going to have a better atom economy just by looking at them before you even do any math. Try and take a guess. Which one? Reaction 1 or reaction 2? Then, after you do that, go ahead and do the math and work it out to try and find which one actually has the higher atom economy. So I'm going to go ahead and get started. If you want to try this on your own, pause the video and just skip to the end where the answers are shown. So, starting with my assumption, looking at these two reactions, I see one byproduct versus two byproducts. Just going by the number of byproducts, I'm going to assume reaction 2 is more efficient. So I'm going to assume that has the higher or better atom economy. So now I'm going to go ahead and work out the math to try and prove that. So for reaction 1, and I'm going to use the steps 1, 2, and 3 from before, the molar mass of the product is going to be sodium, which is 22.99 grams per mole, plus chlorine, 35.45 grams per mole. That's going to make 58.44 grams mole inverse. 2, the sum of the mass of the reactants is going to be, again, sodium 22.99 plus hydrogen 1.01 plus carbon 12.01 plus 3 times our oxygen 16.00. And we're going to add that to our hydrochloric acid 1.01 plus 35.45. My total mass for that is 120.47 grams mole inverse. Step 3, plugging into my equation. 58.44 divided by 120.47 gives me an, times 100 gives me an atom economy of 48.51%. I can already tell that's not very efficient. We want higher numbers than 48%. So moving on to reaction 2. Step 1, it's the same product. So I'm just going to copy that number over as 58.44 grams mole inverse. Step 2, it's a little different here. The sum of the mass of the reactants is going to be 22.99 plus 16.00 for oxygen plus 1.01 for hydrogen plus the same HCl value 1.01 plus 35.45 for chlorine, giving me a total mass of 76.46 grams per mole inverse. Now, before I even do math, I know 58 divided by a lower number than 120 is going to give me a higher percentage. However, I will do the math anyways. Divided by 76.46. That is going to get me, always forget the times 100. I'll be honest, when I do this in my calculator, I never include the times 100 because I just know a percentage moves decimal over twice. But that's 76.43%. So we were right with our assumption. Reaction 2 is more efficient. So the thing I want to end this off with is a discussion on green chemistry. Green chemistry is literally just the focus of sustainable and environmentally friendly, friendly chemical processes. So when we look at green chemistry, something about sustainable and environmentally friendly really catch my eye because that's the main goal. We want to make our product. We don't want to have byproduct that goes into the environment. So if we look at these two reactions up here, we notice we get our product, which is fine because that's what we want. We get water, which we don't actually worry about going into the environment. We can use that water. This can be sustainable in that we can recycle this water for more processes. We can redissolve sodium hydroxide, make more hydrochloric acid solution. We can redissolve baking soda or whatever, or maybe it's drinkable. Maybe we can make it potable. Water is not a bad thing to have as a byproduct. Turns out not all byproducts can be bad. However, I see we get CO2, a major greenhouse gas, as a byproduct of reaction one. So even if this was more efficient, we may still choose reaction two on the basis that we're not producing carbon dioxide gas. So when we talk about green chemistry, while atom economy is a large focus because it helps it make it more sustainable, this environmental friendliness is another aspect we need to look at, whether our byproducts are more or less toxic. So furthermore, this may be a good process because we're getting rid of carbon monoxide, a toxic and powerful greenhouse gas, but we're replacing it with carbon dioxide, which is still greenhouse gas. Maybe there's a better way to get iron out of a chemical process. Maybe we don't need to react rust with carbon monoxide. There might be a more sustainable process. So when we focus on green chemistry, we're focusing on percent yield, we're focusing on atom economy, but we also want to look at the byproducts as well as the reactants we're using, whether or not they are more or less available, whether they're more or less sustainable to attain. So green chemistry takes our raw numbers and adds this level of compassion and also a level of logic and sustainability and this green framework that we're coming to use as much as possible. So I hope all this helps you with DB chemistry and have a great day.